Alsco Limited provides a wide range of products for electrochemistry and spectro-electrochemistry applications, including bipotentiostat, rotating ring disc electrode apparatus and spectrometer system. We also deal in various types of spectro-electrochemical cells, electrodes, and accessories for electrochemical measurement. BAS Incorporated is an exclusive distributor of Alsco Limited products. Where are Alsco Limited and BAS Incorporated located? Alsco Limited and BAS Incorporated are Japanese company, located in the center of Japan, in Tokyo, Sumida Ward. Close to the Tokyo Landmark Tower, Tokyo Skytree. We will quickly introduce you the Alsco Limited product lineup. RRDA3A is an accurate rotator system for hydrodynamic modulation rotating ring disc voltammetry. It has corrosion resistance and compact design and easy operation. It can be operable as ride and RRDE and the rotation speed from 100 to 8000 rpm. Remote and manual control of the rotation and gas purge is possible. Also the spin coating of the electrode. And the speed and purge time can be displayed on the LCD display. It is precisely controlled by pulse width modulation. Electrodes are small and rapidly interchangeable. The unit also provides an adjustable valve system for inert gas purging inside the cell vial. The SEC 2020 spectrometer system is a spectrometer that enables various spectrometric measurements, focusing on spectro-electrochemical measurements. The high-performance grading and optical design makes possible to measure with high sensitivity in a wide wavelength range, from ultraviolet to near-infrared, with a single unit. For the light source, a compact modularized deuterium halogen lamp is used, which is fixed to the cell holder on the accessory platform for the measurement. Furthermore, the spectrometer and the light source come with SMA 905 connector, which makes possible to connect various optical fibers and probes, to construct the original measurement system. ALS also provide electrodes for the basic 3-electrode electrochemical measurement method, such as working electrode. A variety of the working electrodes are available. You can choose according to you the application purpose. For the reference electrode, you can select according to the measurement requirement. A variety of the reference electrodes are available such as silver chloride for aqueous solution, silver ion for non-aqueous solution, and the mercury types are available, which includes the reference electrode for alkaline solution. For the counter electrode, you can also select the suitable one for your measurement purpose. The electrodes introduced here are for the usual static type voltammetry cell. ALS also deal in electrode lineup for flow type. Voltammetry cell for electrochemical measurement. You can select from the lineup depending on the measurement method, sample amount, and combination of electrodes. VC4 for small sample to the measured. SVC2 a multi-purpose cell. SVC3 standard voltammetry cell for 3 electrode with OD 6.0 mm. SVS3C for application at low temperature. And bulk electrolysis cell. Model 2325 is a very low price and high performance bipotentiostat based on modern semiconductor circuitry and advanced software technology. Low noise, high speed, and small space measurement were considerate for the development of Model 2325. The user-friendly interface is designed for supporting wide applications. Model 2325 can be applied in various experiments, such as RRDE, sensor development, and spectro-electrochemical measurements, etc. It can be not only applied for research purpose, but also for student experiments and industrial applications due to the low price and high performance. CS3A cell stand is specifically designed to use a variety of solid electrodes conveniently and cell accessories available from ALS. The working cell is enclosed in a Faraday cage to reduce external electrical interference. A built-in gas control allows purging of the sample. CS3A cell stand features are: reduce the external electrical noise, gas purge function, remote and manual controlled GAR purge and magnetic stirrer, Arrow's remote control from the PC trough, the Potentiostat software, corrosion resistance design. Reversible hydrogen electrode set up using H2G1 portable hydrogen generator. Reversible hydrogen electrode is a kit, in which hydrogen gas is generated by electrolysis of strong acid then stored. It makes unnecessary the complicated and dangerous setup of the hydrogen cylinder and avoids the large volume of hydrogen gas exhaustion, despite that it has a good potential stability. It can be used in a strong acid solution. Also, when using double junction, it may possible to apply in a non-acid solution. Using H2G1 portable hydrogen generator, even without a potentiostat, makes easily to charge the hydrogen gas into the reversible hydrogen electrode kit, and use it as a reversible hydrogen electrode with good potential stability. The practical and safety reversible hydrogen electrode can be prepared by using this instrument for hydrogen gas generation for a reversible hydrogen electrode kit. This prepared reversible hydrogen electrode has high accuracy, stability, and can be the perfect alternative for the traditional standard hydrogen electrode. When using the reversible hydrogen electrode with a double junction chamber, makes possible to apply in a weak or neutral electrolyte solution. The prepared reversible hydrogen electrode can be used in an electrochemical measurement, such as for the RRDE measurement. As an auxiliary function, H2G1 portable hydrogen generator can be used for the potential measurement. Some additional information about BAS and ALS. For the complement of our home page, we have our YouTube channel. In the BAS channel, we have collection of the movies in English, the BAS channel collection, where you can access and watch a variety of the movies, since the product introduction, which includes the product introduction, setup, and troubleshooting, until the technical lectures in the field of electrochemistry and spectroelectrochemistry. In this opportunity, let's follow the BAS channel and watch the movies of a variety of the topics. Also, through BAS channel, the BAS Electrochemical webinar is held online frequently. The BAS Electrochemical webinar is an online webinar which is held frequently by BAS International Sales Team, with their invited lecturers, and it consists of lectures focusing in the field of electrochemistry and spectroelectrochemistry. The BAS webinar is suitable for beginners and for those who want to review and refresh their basic and theoretical knowledge in the field of electrochemistry and spectroelectrochemistry. The series of the lecture was introduced online through the YouTube's BAS channel. The announcement for the future webinar you can have in our ALS website, always on the top page, from which you can jump to the application page, where you will find the detailed information about the schedule and the theme. For any inquiry, please feel free to contact us.
Hello everyone! Thank you for attending the BAS Electrochemical Webinar 2021 December. I'm Miho from International Sales Team, and I will be the moderator. And Today I will also introduce the lecture. Before we start, as unusual, we will ask you to don't be worried to record and enjoy the webinar. We are recording and we will send the directions to you as soon as it is ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start. This video is the second part of the Introduction to Electrochemistry, some basic knowledge. This time, we will introduce you the electron distribution and redox potential of molecules. The second part of this series will introduce the following topics. One of the objectives of electrochemical measurement is to understand the redox potential of the object of study. The redox potential is a characteristic property of the molecules of a substance and can be used for the characterization and identification of the substance. Understanding the electron distribution state of the molecule will be extremely helpful for us to further design substance with the desired redox potential. In order to facilitate the understanding of the electron distribution state in the molecule, let us first review the electron arrangement and atomic orbits outside the nucleus. How atoms form molecules by covalent bonding. The nature of covalent bonding through valence bonding theory. Hybrid orbital theory. Valence electron pair repulsion theory, and the relationship between the shape of the molecule and the electron distribution of covalent bonds. These are requirements to understand the relationship between molecular properties and the valence electron behavior in the context of molecular orbital theory, and further understand the relationship between frontal molecular orbitals, HOMO, LUMO, and redox potential. The number of electrons outside the nucleus is equal to the atomic number, the number of protons, and the number of nuclear charges. The orbital distribution of the electrons outside the nucleus can be described by three quantum numbers. Electron layer, KLMN, which indicate the energy level of each orbital. Electron sublayer orbital numbers, SPDF, which indicates the angular momentum of each orbital motion. Angular momentum of orbit observed in the direction of the external magnetic field. The arrangement of electrons in atomic orbitals follow three basic theorems. The principle of minimum energy. When the electrons outside the nucleus are moving, they always preferentially occupy the orbitals with low energy, so that the whole system is in the lowest energy state. The Pauli incompatibility principle. Each orbital can accommodate at most two electrons with opposite spins. Hundi's rule. When electrons are arranged in degenerate orbits, they will occupy different orbitals as much as possible, and their spin will be parallel. For the same electron sublayer, when the electron arrangement is full, half full, and it is relatively stable when it is completely empty. According to this principle, the outer electron arrangement of atoms with atomic number 1 to 30 is shown in the figure 2.1. Since the energy of the outermost electron of an atom is higher than that of the inner electron shell, The distribution of electrons on the outermost shell determines the chemical reactions properties of this atom. The electron sublayer orbital shapes are S. Orbital are spherical. P. Orbital are dumbbell-shaped, distributed along the x, y, and z axes, called px, py, and pz orbitals. There are 5 types of d orbitals: dxy, dxz, gyz, dz2, y2, and the unique shaped dz2 orbitals. When forming a molecule, atoms attract shared electrons. The attractive force of an atom for a shared electron depends on the type of element. The strength of attracting electrons shared by atoms is called electronegativity. Here, some examples of molecules with a nonpolar and polar bonds. The former hydrogen molecule is a polar molecule because the 2 hydrogen atoms have the same electronegativity. For the carbon dioxide molecule, the carbon and oxygen bonds are polar bonds, but because of the linear symmetry of the molecule, the entire molecule is nonpolar. The methane molecule is also nonpolar because of its tetrahedral symmetry. The electronegativity of chlorine atom in the hydrogen chloride molecule is much higher than that of hydrogen atom. So it attracts the shared electron toward the chloride side, making it a polar molecule. A water molecule consisting of 2 hydrogen atoms and 1 oxygen atom is a polar molecule because the angle between the 2 hydrogen and oxygen bonds is 104 degrees. So the oxygen atom side has a small dipole charge and the hydrogen atom side has a large dipole charge. The ammonia molecule has a triangular pyramidal shape, and it's a polar molecule. Chemical bonds in molecules can be classified into 3 main categories. Ionic bonds. The interaction between oppositely charged ions are called the ionic bonds, generally between metals and nonmetals. Metallic bonds. The electrostatic attraction between free electron and metal ion arranged in a lattice form to form bonds that exist mainly between metal atoms. Covalent bonds. It is the interaction between atoms, usually bonding between non-metal atoms, formed by shared electron pair, overlapping electron clouds. Here, there are various classification methods of covalent bonds. First, according to the number of shared electron pair, there are single bonds, double bonds, and triple bonds, etc. Second, according to whether the shared electron pair is shifted or not, there are polar bonds and no polar bonds. Third, according to the method of providing electron pairs, there are normal covalent bonds and coordination bonds. Shelled electrons pair are provided by one part and empty orbitals are provided by other part. For example, one of the nitrogen and hydrogen bonds in the ammonium ion is a coordination bond. Fourth, according to the overlap of electron clouds, there are sigma bonds. The electron clouds are bonded in the direction of the bond axis. In a head-to-head, for example, carbon-carbon single bond, and phi bonds. Electron clouds along both sides of the bond axis in the direction of shoulder to shoulder. For example, carbon-carbon double bond has a sigma bond and phi bond. According to the conventional Lewis covalent bond theory, it is recognized that molecules are formed by sharing electrons between atoms of the same element or between atoms of elements with similar electronegativity. The chemical bond formed by sharing electron is called a covalent bond, and the molecular form is called a covalent molecule. Two connected atoms in a molecule share one or more electrons pair in order to achieve an electron configuration similar to that of an inert gas atom, thereby forming a stable molecule. This concept is known as the Octet Rule. However, Lewis' theory does not explain the nature of this bond and has its limitations and its adaptability. For example, the extranuclear electron of the boron atom in the boron trichloride molecule and the phosphorus atom in the phosphorus pentachloride molecule do not conform to this theory, so the molecular structure cannot be interpreted. Compared with the conventional Octet rule of Lewis theory, valence bond theory inherits the concept of covalent bonds, and at the same time, based on quantum mechanics, it assumes that the electron spin of a covalent bond is in the opposite direction. The electron further clarifies the nature of covalent bond and allows for a more experimental interpretation of the phenomenon. The saturation and directionality of covalent bond can also be further interpreted, and some phenomena that cannot be explained by conventional Lewis theory can be resolved by hybrid orbital theory and investigated structure theory. In the quantum chemical model of valence bond theory, the essence of covalent bond is the overlap of orbitals between atoms in close proximity, and the bond is thought to be formed between atoms by lowering their energy by sharing electrons pair with opposite spins. The electron cloud overlap along the direction of the connecting lines of the nucleus, resulting in an asymmetric electron cloud image. This covalent bond is called a sigma bond. In simple terms, a sigma bond is formed when two atomic orbitals overlap head to head. If the electron cloud image obtained after the electron cloud overlap is mirror symmetric, this covalent bond is called a pi bond. In other words, a pi bond is a bond formed by shoulder-to-shoulder superposition of two atomic orbitals. Generally, if there is only one electron pair between atoms, the covalent bond formed is a single bond, usually a sigma bond. If the covalent bond between atoms is a double bond, it consists of one sigma bond and one pi bond. In the case of a triple bond, it consists of one sigma bond and two pi bonds. The sigma bond can be formed between SS, SP, PP, and other electrons, and the pi bond can be formed between PP, DP, DD, and other electrons. In addition, there are very diverse types of covalent bonds, such as PP large pi bonds in benzene ring and DP large pi bonds in sulfate radicals. To further interpret the relationship between molecular shape and covalent bond, in 1931, Pauling proposed a hybrid orbital theory based on valence bond theory. This theory is still basically a part of modern valence bond theory, but it has evolved modern valence bond theory in terms of bonding ability and spatial arrangement of molecules. In short, in the process of bonding, due to the interaction between atoms, several types of atomic orbitals with the same energy in the same molecules are linearly combined to redistribute the energy and the spatial orientation. Distribution may occur and the same number of atomic orbitals can be formed. Such recombination of orbitals is called hybridization, and new orbitals formed after hybridization are called hybrid orbitals. When one s orbital and three p orbitals in the outermost orbital of the second period element are sp3 hybridized, four degenerate hybrid orbitals of the same energy are formed. The theory of hybrid orbitals can easily explain the tetrahedral structure of the methane molecule. The carbon atom of methane molecule, when the nitrogen atom of the ammonium molecule, and the oxygen atom of the water molecule all form a covalent bond with the hydrogen atom via the sp3 hybrid orbitals. The arrangement of electrons in the four sp3 hybrid orbitals degenerate is shown in the figure. Carbon, nitrogen, and oxygen atoms can form covalent bonds with each other as well as with hydrogen atoms to form a variety of organic molecules through sp3 orbital hybridization. For example, the carbon-carbon and carbon-hydrogen bonds in the ethane and methylamine molecules are covalent molecules composed of nitrogen-hydrogen, nitrogen-carbon, and carbon-hydrogen bonds. The familiar ethanol molecule has four covalent bonds as carbon-carbon, carbon-oxygen, carbon-hydrogen, and oxygen-hydrogen. The outermost shell orbital of the second period element can also be an sp2 hybrid orbital. Two mutually perpendicular p orbital and one s orbital forms three equivalent sp2 hybrid orbital. The geometry of electron orbital is shown in the figure. The energy of three hybrid orbital is lower than that of the pz orbital. The orbitals of outermost shell of the carbon element after sp2 hybridization are 1 pz orbital with a reduced energy level and 3 sp2 degenerate orbital. The four outermost shell orbit electrons are arranged in four orbitals with the same spin direction. The nitrogen has one more electron than carbon, so this electron can also enter the sp2 hybridization orbital by overcoming the energy of the pair. Hydrogen has one lone electron pair. The oxygen element has one more electron than the nitrogen element, so this electron can also enter the sp2 hybridization orbital via one pair, and the oxygen element has two lone electron pairs. The sp2 hybrid orbitals are distributed on the same plane, and the remaining pz orbital is perpendicular to the plane. The two sp2 hybrid orbitals form bonds with two hydrogen atoms, and the remaining one sp2 hybrid orbital is connected to the sp2 hybrid of another carbon. The chemical orbital overlaps sigma head to head, to form a sigma covalent bond, and the remaining pz orbital forms a pi covalent bond with the pz orbital of another carbon by shoulder-to-shoulder overlap. Similarly, nitrogen and oxygen atoms also pass through the sp2 hybrid orbitals to form hydrazone molecules with nitrogen-nitrogen double bond and formaldehyde molecules with oxygen-carbon double bonds. Carbon-carbon, nitrogen-nitrogen, oxygen-carbon double bonds cannot be rotated due to the formation of the pi bonds. Let's look at a more special sp2 hybrid orbital molecule benzene. We know that organic compounds, benzene molecules, and their derivatives basically do not undergo addition reactions that lose the structure of benzene ring, but undergo substitution reaction of remaining benzene ring, such as nitration, sulfonation, halogenation, Friedkraft acylation, alkylation, and other substitution reactions. This is due to the fact that the benzene ring is formed by one of the sp2 hybrid orbitals on the carbon atom, forming a carbon-carbon sigma bond with the sp2 hybrid orbitals on the other atoms, and the remaining pz orbital forming a pi bond with the pz orbital of the other carbon. It has been found that benzene is a resonant mixture of these two extreme structures, which can be expressed in this form, and this expression, when compared with the length of the carbon-carbon bond in the benzene ring and the typical carbon-carbon single bond and carbon-carbon double bond, shows that the bond length is between the two at 1.39 angstroms. The reaction of benzene and its derivatives are residual substitution reaction of benzene ring. Therefore, understanding the electron distribution state of molecule is very useful for understanding the property of the chemical reaction of the molecule. Next, let's look at an acetylene molecule with a sp hybrid orbital. When the outermost orbital of the carbon atom are hybridized by the sp orbitals during the formation of the molecule. The orbitals and electron arrangement are shown in the diagram. One of the sp hybrid orbital forms a carbon-carbon sigma bond with another sp hybrid orbital of carbon. The remaining sp hybrid orbital forms a carbon-hydrogen sigma bond with a hydrogen atom, and the remaining pz and py orbitals overlap shoulder to shoulder with another carbon atom pz and py respectively. Acetylene molecule forming two pi bonds containing carbon-carbon triple bonds are linear molecular. It is very convenient to assemble molecules with atomic units using the valence bond method. For example, the single bond sp3 unit, double bond sp2 unit, triple bond sp unit, and these single electron orbitals units can be combined to obtain various combinations of molecules, which will help us to understand the molecular structure. Valence shell electron pair repulsion theory combines the concept of shared electron pair and lone pair electron with the concept of atomic orbital, considering the shape of the molecule according to the number of electron pair, which further improves the modern valence bond theory. In this model, the electron pair repel each other and the bonding electron are as far away from the lone pair as possible. The shape of the molecule is considered in terms of the number of the electron pair. The main points of this theory are: electron pair repel each other in spatial position as far away from each other as possible. Electron pair can be divided into the bonded electron pair and lone pair. The magnitude of the repulsive force between electron pair is great between the lone electron and small between the bond electron. According to this theory, it can be considered that when the number of electron pair is 2, linear molecules are formed. When the number of electron pair is 3, it's a trigonal plane. And when the number of electron pair is 4, the Octet Rule is satisfied and the molecular shape is tetrahedral. When the number is 5, the molecular shape is trigonal bipyramidal. And when the number of electrons is 6, an octahedral molecule is formed. The valence shell electron pair repulsion theory is the simplest way of visualizing chemical change and make it easy to determine the spatial configuration of substance. Let's look at this molecule with 4 pairs of electrons. In the metal molecules, the 4 electrons pair are all bonding electrons pair, and the repulsion between the electrons pair is the same. Because of the 4-plane geometry of metal molecule, the angle between each carbon-hydrogen bond is the same, 190 degrees. In the ammonia molecule, one of the 4 electrons is a lone electron and the other are bonding electrons. The repulsive force between the lone and bonded electron is greater than the repulsive force between the bonded electron. So the space between the bonded electrons is compressed and the angle between the nitrogen-hydrogen bond is reduced to 107 degrees. In the water molecule, there are 2 lone pairs of electrons, and the repulsion force between them is large. The space between the 2 bonding electrons is further compressed and the angle between the 2 hydrogen-oxygen bonds is further reduced to 104.5 degrees. Molecular orbital theory is also called the molecular orbital method, or MO method. In 1932, American chemist Mulliken and German physicist Hand proposed one of the modern covalent bond theories. According to molecular orbital theory, when an atom forms a molecule, every electron in the atom contributes to the molecule. The electrons in the molecule no longer belong to the atom, but are distributed throughout molecular space. The spatial motion of the electrons in a molecule can be expressed by the corresponding molecular orbital wave function psi. The main difference between molecular and atomic orbitals are following. In atoms, the movement of electrons is only affected by one nucleus, and the atomic orbital is mononuclear system, while in a molecule, the electron moves under the action of a potential field of all the nuclei, and the molecular orbital is a multinuclear system. The linear combination of wave functions of atomic orbitals forms a molecular orbital. The psi molecular orbital contains bonded orbitals and antibonded orbitals. The molecular orbital formed by overlapping atomic orbitals in phase are bonded orbitals and are relatively stable due to the orbital energy level drop, and the molecular orbital formed by overlapping antiphase orbitals are antibonded orbitals and relatively unstable due to the rise in the orbital energy level. In general, atomic orbits are represented by SPD symbols, and molecular orbits are represented by sigma, pi, delta symbols. Molecular orbits are created by the linear combination of atomic orbits in a molecule. If there are several atomic orbitals, the same number of molecular orbitals can be created. Molecular orbital formed by the superposition of two in-phase atomic orbitals with matching symmetry increase the density of electrons between the two nuclei, and the energy of orbitals is lower than the energy of the original atomic orbitals. Such molecular orbitals are suitable for the formation of bonds and are called bonded molecular orbitals. The sigma bonding orbitals of SS, PP, and SP, and the pi bonding orbitals of PP, asymmetric orbitals as shown in the diagram, appears to be of this form. At the same time, if these two orbitals with matching symmetry are also subtracted, by the way, they overlap in opposite phases, and another molecular orbital is formed. The probability of electron density between the two atoms becomes very small. The orbital energy is higher than the original atomic orbital energy. Such molecular orbitals are detrimental to bond formation. It is called the antibonding molecular orbital. The shapes of the sigma antibonding orbitals of SS, PP, SP, and the pi antibonding orbitals of PP are true to be like this. To distinguish between antibonding and bonding orbitals, a star symbol is often added to the symbol of the antibonding orbital. There are also special cases where the spatial symmetry of the atomic orbitals that makes up the molecular orbital does not match, and the atomic orbitals do not effectively overlap. As a result, such molecular orbitals are called unbound molecular orbitals, because the energy of the bound molecular orbitals is not much different from the energy of the atomic orbitals. In the hydrogen molecule, the semi-phase orbitals of the 1s orbitals of two hydrogen atoms overlap to form a bond molecular orbital. The electron crowd density between the two nuclei increases. The energy level of the bonded molecular orbital is lower than the original atomic orbital. The reduced energy is called the stabilization energy. At the same time, the antibonding molecular orbitals of the 1s orbital of the two hydrogen atoms overlap to form an antibonding molecular orbital. The density of the electron crowd between the two atoms decreases, and the energy of the antibonding molecular orbital increases. And the energy that is higher than the original atomic orbital energy level is the destabilization energy. Two 1s electrons enter the lower energy bonding molecular orbital, forming a hydrogen molecule. The arrangement of the electrons in the L layer of the fluorine atom is 2s, 2px, 2py, 2pz. The 2pz orbitals of the phase of the two fluorine atoms in the fluorine molecules overlap along the line connecting the two nuclei to form a sigma bonding orbital. The tan electron in the 2pz orbitals enter the sigma bonding orbitals of pp and fluorine molecules are formed. The overlap between orbitals is only possible when the symmetry is the same, and there is no interaction between orbitals with different symmetry. A is the interaction between bonding and antibonding orbital for the sigma interaction. B is the interaction between bonding and antibonding orbitals for pi interaction. C, no interaction between orbitals with different symmetry. The greater the overlap between orbitals and the orbitals, the more stable the bonding orbitals are. The more unstable the antibonding orbitals are, and there is no interaction between orbitals with different symmetries. The outer molecular orbitals of the nitrogen molecules and oxygen molecules and their electron arrangement are shown in the figure 4.6 and 4.7 respectively. Since each nitrogen atom contains 5 electrons, the nitrogen molecule contains 10 electrons. Similarly, the oxygen molecules contain 12 electrons. The bond order between two atoms when forming a molecule can be calculated according to number of bonded electrons minus number of antibonded electrons. Since the 2s-2s atomic orbitals form 2 electrons in the sigma bonding orbitals and 2 electrons in the sigma antibonding orbitals, the bonding number is 0, which means that these two molecular orbitals do not contribute to the bonding of the molecule. In general, the energy level of a sigma bonding orbital formed by the combination of two pz orbitals should be lower than that of pi bonding orbital formed by the combination of two px or two py orbitals, like the molecular orbital distribution in oxygen molecules. In the nitrogen gas molecule, there is a different situation. For a mononuclear diatomic molecule with a small nuclear charge like the nitrogen atom, the splitting wide of the pi antibonding or orbital energy level is the molecular become larger, and the energy level of the two pi bonding orbitals formed will be lower than the energy level of the sigma bonding or molecular orbitals formed by the two pz atomic orbitals. So the valence electron in the molecule will enter the two pi bonding orbitals in order of preference, and the last two electrons will enter the sigma bonding molecular orbital. By subtracting the number of electrons in the bonding orbital from the number of electrons in the antibonding orbital, 6, and dividing by 2, the number of bonding in the nitrogen molecules is calculated to be 3. The figure shows that the highest occupied molecular orbitals in the nitrogen molecule is the sigma bonding molecular orbital, and the electrons are paired to form a stable chemical bond. The energy level of sigma bonding molecular orbital formed by the 2pz atomic orbital is lower than that of 2 pi bonding molecular orbital formed by the 2px and 2py atomic orbitals. The arrangement of the 12 valence electrons in the molecular orbitals is shown in the figure. The highest occupied orbital in the oxygen molecule is the antibonding pi orbital, which has a higher energy than the px-py atomic orbital energy level of the atom, and the electrons of a 2-pi orbital are prone to gain or lose to form oxygen ion, superoxide ion, peroxide ion are the forms. The number of valence electrons, unpaired electrons, bonding number, bond length, and bond energy, etc. are indicated here. The outer molecular orbitals of elements of second period forming diatomic molecular can be divided into two groups. The molecular orbitals of the lower nuclear charge group, lithium, nitrogen, are the same as those of nitrogen molecular, and the splitting energy of the pi orbitals is higher than that of the sigma orbitals. Since the L layer electron number of beryllium is 2s2, when 2 of the 4 valence electrons enter 1 sigma gerade and 2 electrons enter 2 sigma ungerade antibonding orbitals, there is no change in energy and it is an antibonding molecular orbital, and the bonding number is 0. So, there is no beryllium diatomic molecule. The molecular orbital of oxygen and fluorine with high nuclear charge have the same type of distribution, and the splitting energy of the sigma orbitals is higher than the splitting energy of the pi orbital. The relationship between molecular orbitals and atomic orbitals of diatomic moleculars is described below. Figure 4.9 shows the relationship between molecular and atomic orbitals of Ba-type moleculars. P is an atom with low electronegativity, and A is an atom with high electronegativity. The figure shows that atoms with high electronegativity contribute significantly to the bonding orbitals. Here, atoms with low electronegativity are used in large number of antibonding orbitals. Energy difference is not as large as that of a diatomic molecule. Energy difference increases as the energy difference between atomic orbitals decreases and the orbital overlap increases. The orbital of hydrogen fluoride molecules are shown in the figure 410. The L-layer orbital of the fluor atom with high electronegativity has a low energy level than the K-layer orbital of hydrogen atom with lower electronegativity, and the total number of electrons in the two atoms, which the sum is 80, enter the following molecular orbitals respectively. The molecular orbitals of nitric oxide are shown in the figure 411. The left side shows the orbital of nitrogen atoms with low electronegativity, and the right side shows the orbitals of oxygen atoms with high electronegativity. The 2s atomic orbitals form sigma bonding and sigma antibonding orbitals. The 2pz orbitals form sigma bonds and sigma antibonding orbitals, and the px and py orbitals form two bonding pi orbitals and two antibonding pi molecular orbitals. The 2px and 2py orbitals form two bonding pi orbitals and two antibonding pi orbitals. A total of 11 electrons in the molecular are arranged in the molecular orbital in this way. The electron-occupied molecular orbital with the highest energy level is the pi or antibonding orbital, since there is only one electron in this orbital. This orbital is called a sum. single occupied molecular orbital. The arrangement of the electrons in the nitric oxide molecule indicates that the nitric oxide molecule is prone to electron gain and loss. The bond state of the nitric oxide molecule is 2.5 double bonds. If the nitric oxide molecule loses one electron, it becomes a nitric oxide plus ion, and the bonding force becomes a triple bond. When the nitric oxide molecule gains one electron, it becomes a negative nitric oxide ion. The bonding factor is a double bond. The arrangement of electrons in the molecular orbitals and the energy level of the electrons can be used to predict the gain or loss of charged molecules in the molecule and hence the tendency of redox reaction. The orbitals of carbon monoxide molecule are shown in the figure 4.13. With the atomic orbitals of the relatively less electronegativity, nitrogen atom on the left and the more electronegative oxygen atom on the right. The energy level of the pi bonding orbitals are lower than those of the bonding orbitals, and the energy level of the pi antibonding orbitals are lower than those of the sigma antibonding orbitals, due to the larger difference in electronegativity between the two atoms and the difference of the two atomic planes. The 10 orbitals of the molecules are thus arranged in the molecular orbital. The electron-occupied molecular orbital with the highest energy level is the sigma bonding orbital, which lowers the molecular or electron energy level and makes it stable. The energy level of the pi-bonded molecular orbitals shown in the figure 4.14 are lower than those of sigma-bonded molecular orbitals. The electron donating property, that is, electron donor property, of the bonding molecular orbital increases from right to left, while the electron accepting property of the pi bonding orbitals increases from right to left. When considering the redox reactions, it can be reducing agents and oxidizing agents, respectively. The orbital distribution of the molecule or electrons can be used to predict the gain or loss of electrons in the molecule, that is, the tendency of redox reaction. Frontal orbital theory is a chemical reaction theory published in 1952 by Dr. Kenichi Fukui, the first Nobel Prize in Chemistry in Japan. The achievement was a milestone that would deepen our human understanding of chemical reactions. Until then, the understanding was very low. Before that, it was the organic electron theory of Robinson, Nobel Prize winner in 1947, and other that was understood. So, the main attempt to understand it was through the attraction of positive and negative charges. The frontal orbital theory was born in the 20th century with the birth of quantum mechanics. The secret of success lies in the fact that the orbitals of electrons will reflect the nature of electron waves. In organic molecular reactions as HOMO, highest occupied molecular orbital, in the reductant molecular, and LUMO, lowest unoccupied molecular orbital, in the oxidizer molecular, interact with each other, and the delocalization of electrons occur and redox reactions take place. When molecules are close to each other, their molecular orbital overlap and interact with each other. When two orbitals interact, 1. They transform into two orbitals with lower and higher energy than the original orbitals. 2. The formed low-energy orbitals overlap in the same phase and the electron density increases. 3. In the higher energy orbitals, the interacting orbital overlap is opposite phase, which decreases the electron density in the overlapping region. Thus, when an orbital containing two electrons interacts with an empty orbital, both electrons enter the stable orbital and destabilization occurs. The smaller the energy difference between the interacting orbitals, the higher the degree of stabilization. Therefore, the Ohm-Luhm interactions contribute the most to the stability of the transition state. Before the Ohm-Luhm interaction, the electrons located in the Ohm mix with the Luhm after the interaction, so they localize to the partner molecule. Electron delocalization is also important for molecular stability, and it is a concept that forms the basis of chemistry. Based on such concept, electrochemical oxidation reactions can be considered as the loss of electron in Ohm and reduction reaction as the gain of electron in Luhm. Here is a schematic diagram of the relationship between the frontal molecular orbitals Ohm and Luhm and the redox potential of molecules. When the electrode potential changes in the direction of the negative potential, the Fermi electron energy level on the electrode rises. When the Fermi energy level is higher than the Luhm, the electron on the electrode will enter the Luhm of the molecule, causing such a reduction reaction. Conversely, as the electrode potential moves towards the positive potential, the Fermi level of the electron on the electrode decreases. When the Fermi level is lower than the Ohm, the electrons on the Ohm of the molecule move to the electrode, and the oxidation reaction occurs. Understanding the Ohm and Luhm of molecules and the electron arrangement of their orbitals is important for predicting whether a molecule can undergo an oxidation or reduction reactions and the direction in which the reaction will proceed. Oxygen is one of the most important elements on Earth. Life activities on Earth cannot be carried out without oxygen. In the study of fuel cells, the reduction reaction of oxygen is very important. Through molecular orbital theory, it is possible to study and understand the arrangement of electrons of oxygen molecules on molecular orbital. Let's look at a well-known example of reaction between oxygen and hydrogen. When hydrogen gas is injected from a burner into the air and ignites, it burns with an almost colorless flame, producing water. The chemical reaction is shown in the equation 1. The reduction reaction of oxygen in an aprotic organic solvent, such as acetonitrile and dimethylformaldehyde, has two stages of electron reduction as shown in equation 2. The oxygen molecule is first reduced to form a superoxide ion and reduced to obtain electrons that form peroxide ion. Figure 5.3 shows a cyclic voltagram of molecular oxygen dissolved in pyridine. The cyclic voltagram makes it easy to understand the relationship between the redox electron process of molecular oxygen and the electron arrangement of the molecular orbital. And figure 4 shows the schematic diagram of oxygen atomic orbital and oxygen molecular orbital energy level distribution and electron arrangement. The contents of this introduction are summarized as follows. Here, understanding the electronic states of the frontal molecular orbitals of molecules is crucial to control the future direction of electrochemical reaction of substances. This concludes the second part of the introduction to electrochemistry, basic knowledge, electron distribution, and redox potential of molecules. If you have any question regarding to the lecture or other topic, please feel free to contact us. The email is here. Also, we will be sending the direction to watch and review this webinar. Also, you can watch here in the BAS channel a variety of movies which you can follow and have access to the latest news, including the past webinars. The next webinar we are working out to have for February. Lastly, thank you for enjoying our activity this year, and we wish you and your family a health, happiness, peaceful and joyful holiday and a wonderful new year. For today, thank you again, and stay safe and healthy.